So welcome everyone to the last forum of the semester on the last day of November, on the second to last day of classes. Thank you all for making it here. I'm sure everybody's very busy with end of the semester preparations. I have some notes I'm going to check. Oh, first of all, so in case any of you don't know me, I'm Laura Tadioshin. I'm core faculty here in the Center for Geospatial Analytics. And today I'm very pleased to be hosting Dr. Andrew Wilson from the Sandia National Laboratory in Albuquerque, New Mexico. Let's see, what else did I want to say? Oh, yes. So before he started at Sandia, he earned his PhD at, cover your ears, football fans, UNC Chapel Hill in the computer science department. And he worked under Dinesh
Minocha, yep.
Okay. So not only does he come from a long line of tenacious stock, ask him about his ancestor that fell off of the Mayflower.
He actually did.
His research includes large data analysis from the point of data curation to visual analytics. And he's also interested in cybersecurity, topic modeling, visualization, information visualization, graph analytics, graph analysis. That's the graphs, GIS 540 students. That's the graphs that you're learning about, yes? And let's see, one of the many things that Andy's research, all of his research interests have in common is the importance of the spatial context, as we were discussing
well spotted
earlier. So with this, I will let Andy tell us about his fascinating research on munching through the spatial spaghetti that is aircraft.
Thank you very much, Laura. I told her that if it didn't look interesting enough to just make things up. I'm not going to tell you which ones of those might be made up. Instead, I'm going to tell you about a research effort we've had running in, hey camera, yes, I'm over here, in trajectory analysis and classification. This work started about 5 years ago with a large project we called Panther, which was about an analysis of patterns of life in any kind of remote sensing data, imagery, trajectories, transponders on whales or livestock. It turns out that cows are highly Brownian. So what kind of milk Brownian cows produce, I don't know. Anyway, when we look up at the sky and see an airplane, this is what we see about air traffic. Almost always a single airplane, almost always either on approach or taking off. It's a very simple, deceptive view. Here's the reality of it. This is a heat map showing, I think, a week of air traffic over the continental U.S. and part of the Caribbean. Yes, there's structure there if you care to look at it. The actual image shows you more detail than this monitor is capable of reproducing. I'll have the slides available to you next week. But you know, even this omits a lot of the useful information. So the question is, how do we make sense of this? How do we take this mess, which is one day around DC, this isn't even a bad one, and turn it into patterns that we can think about, that we can reason about, that we can model, and try to decide, does this reflect reality? That work is what I'll be talking about today. This is ongoing research. It started 5 years ago, but it's got plenty of momentum. So first, before I can tell you about data analysis, let me tell you about the data. There is a data feed that comes from the FAA called Aircraft Situation Display to Industry, ASDI, which I'll call ASDI for short. It is an unclassified feed that comes from the US FAA. It contains non-sensitive civilian air traffic, and aviators can opt out of that if they choose for privacy concerns. But practically speaking, it includes every commercial aircraft any of us are ever likely to fly on, as well as lots of air cargo traffic, lots of small private jets, and even some more interesting operations that I'll point out to you presently. As data sets go, as real world data sets go, this is one of the cleanest ones I've ever seen. We get anywhere between 30,000 and 65,000 flights per day, mostly flights that have filed instrument flight plans. And what happens is every aircraft is in constant communication with a ground station. It reports its position, its vital statistics, it's actually more frequent than the 5 seconds I list here, every 2 to 60 seconds. That information gets aggregated at the FAA and then reported out to subscribers to that data feed with a position report for every aircraft every 60-ish seconds. And that's pretty constant. It is, by some standards, a lot of data. About 5 million points a day, comes out to a little over a gigabyte of XML. By some standards, that's actually very small, but trust me, it adds up fast. And a lot of metadata. We get 17 columns for each of those reports, ranging from the flight ID to the origin and destination airports. Sometimes we know exactly what kind of airplane it is. Sometimes we know the tail number of that airplane, so we can tell you, no, that airframe belongs to Bob. And sometimes we have a long encoded string representing the flight route. But we always have ID, timestamp, latitude, and longitude. The analysis I'm going to be showing you today uses just those 4 quantities. There is certainly room to incorporate others in the algorithm. Like I said, this is ongoing research. So, suppose you are someone whose job is to watch the airspace and pinpoint things that are not right, or pinpoint weird things. The way they do this, if you are an air traffic controller, is they sit you in front of a monitor. They say, this is such and such chunk of airspace over, say, Missouri. Go. Let's see if that works for us. This movie, so I'll pause it for a moment. This is Chicago. Lake Michigan, the city of Chicago is right here. Now I'm just going to let this run. I want you to watch it. There will be a quiz. No, this is not fair. Watch it anyway. Yes, blue means descending, so the blue flights are coming in for a landing. Orange means climbing. Orange is usually departure. White is just passing through, so it's level flight.
Does this include commercial and private?
Yep.
With no military traffic, right?
It is air traffic.
No military traffic.
No military traffic.
You mentioned latitude and longitude. Do you have altitude?
I do. I am deliberately not using it. I used it to calculate the colors, but apart from that, no. The reason for that, by the way, is that the algorithms we developed can be used on maritime traffic as well as air traffic. If the altitude of your maritime traffic is anything other than 0, you've got something really interesting going on. Okay. What did you see? Speak up.
Daily travel for O'Hare and Midway.
Okay, you saw daily travel for 2 major airports right next to each other in the center of the image. What else did you see?
Several sort
are streams, if you will, rivers of flow that people are entering and exiting from.
Several coherent paths of traffic, typically leading into and out of those airports, but there are also a couple of paths for people passing through from like Milwaukee headed south.
You had a wind from the west, because everything was landing into a headwind.
Well spotted. Did you see the wind change?
Yes, that happened in the early part.
The wind changes in the early part. You can tell that because aircraft, if they have any choice at all, will always take off and land facing into the wind. And when the wind changes, it typically means a brief shutdown, brief meaning 20, 30 minutes if you're lucky, while ramp control at that airport manages the traffic jam of getting everyone from this runway to that one. You are the first gentleman to ever point that out in this data set. Congratulations. What else did you see?
That must be an airport north of this image that you don't see, because I saw a lot of flights that are kind of,
Yep.
it looks like they were rising.
Yes.
And they came from north. So
Yes.
That must be an airport right
Milwaukee is just off the top of this movie. Yes, sir.
There were a handful of flights that circled around like 10 times.
There were a handful of flights that just sit and circle a bunch. I'm sorry? There was one particular anomaly. There was one flight that does something unlike any other in this entire data set. I'm going to show you that in a moment. But first, the point about the wind changing is so dramatic once you know to look for it that it's worth going back and playing. See these streams? These are coming into O'Hare. Watch them. You will see them change. Right there. The wind has changed, and now everything's landing to the west. And I guarantee you it was a royal mess on the ground at O'Hare when that happened. All right, I'm going to play this same movie again, but with one particular trajectory highlighted. You're going to see it here in the lower right-hand corner of the screen. You will know it when you see it. It is a thick, bright line. Here we go. I assure you, this was in the original movie. There it is.
It's a live flight.
Aerial photography. Aerial photography, right?
Such a big area to be playing on. Is he really wiggling?
I don't know. It's possible that that's just imprecision in the measurement, but he is going up north and south and north and south, and that one trajectory looks absolutely nothing like anything else in this data, but no one sees it. That's because you're not looking for it. You don't know to expect one of those. It's not in the central data flow for Midway and O'Hare that draws the attention visually, and yet the current practice is to just sit humans in front of these displays and have them watch, not even sped up, in real time, and expect them to pick out these anomalies. In all the times I have given this talk to audiences large and small, 8 people have ever spotted that flight. All of them were pilots. Well, we can do better than that. We want to find out where these anomalies are, whether or not we know what they are ahead of time, and try to figure out what are they doing. Here I've got still images of the same thing just to drive home the point that this is a lot of structure and it's not possible to see everything in it without assistance. Now, that flight really is here. It's hard to see unless you've got much better vision than I do, but faint vertical lines really are there. Anyone care to guess what that is? Okay. Bingo. That aircraft is a Twin Otter, which is a little propeller jet with a propeller, I believe, on each wing, and a hole cut in the bottom of the fuselage with a camera in it. When you go to your favorite digital mapping site and zoom in to the point where you can see, like, you can almost figure out what model of car it is, those pictures were taken by one of these aircraft. There's a couple of dozen across the U.S., and when you dig into the data, you find out these mapping flights are everywhere. In fact, they're so common that they're not really an anomaly. They're just a common class with very few examples. And what's more interesting, they always fly north to south. As far as I can tell, this is not written down anywhere, but the people who first flew those kinds of survey flights decided, yeah, north to south, why not? The only case where that changes is when they are doing close photography of a city whose street grid is lined up differently. So you look at parts of Los Angeles, and they will fly at an angle about 20 degrees off north and south, so that they can look down at the streets instead of just seeing the sides of buildings. That was the easy one. This is one of the data sets we really care about. This is one day over the United States. Same color scheme, blue is landing, orange is taking off. You can see the major hubs, you can see the major traffic corridors. You cannot see anything that's on the scale that you actually want to find. Hopefully by now I've convinced you that this is a problem that human analysts can't get a grasp on, and so we need algorithmic assistance. Great! I'm a computer scientist. We've been doing machine learning for 30, 40 years. We have plenty of algorithms for finding groups of things. Well, there's a problem. Almost all of the clustering algorithms require what's called a vector space for their trajectories. A vector space means that if I have points A and B, I can tell you how far they are apart, and I can tell you how to get from A to B. A trajectory is just a parameterized curve in space. It lives in what's called a non-normed metric space. I can tell you how far apart A and B are, but I can't tell you how to get from here to there. That means that our 40 years of clustering algorithms, just as they're written, won't work, or if we're lucky, they work but take much, much more time. Those are the trajectory comparison functions that I mentioned in the first part of this slide. They tend to come from applications like handwriting recognition. Let's say let's say you're the post office. I give you a squiggle of 5 little symbols. You want to turn that into a zip code. Well, you know a lot about that squiggle when you just start. You know about what size it's supposed to be. You know one of 10-ish combinations that it's supposed to be. And that's a relatively straightforward decision process. These trajectories are nowhere in that class. Sequence alignment and dynamic time warping. These come largely from genetics. Given 2 sequences of proteins with holes in them, yeah, you can kind of stretch and squash to find the holes and line them up. We can't do that either. Last and not least, in order to do clustering effectively on this kind of data, we have to run in a vector space, which is a subset of, a vector space is a subset of a metric space, and we have to, because we need enough memory. There are, like I mentioned, if you really want them, clustering algorithms that will run without it. They take a an awful lot of space and memory. Now for an application like this, yeah, you can get a well-equipped workstation to run on if you can make a convincing argument to your department head. Can you get the large supercomputer you would need to run metric-only clustering on millions or billions of trajectories? No, not unless you're already at a national lab, in which case you're not sitting in this audience, you're me. So, most of computer science can be cast as intelligent applied laziness. I do not want to work in a non-normed metric space. I want to bring this back into a vector space so that I can take advantage of the work of 40 years of people who are much smarter than I am. Like I said, applied laziness. So what we're going to do is we are going to invent features for these trajectories that in some numeric fashion describe its behavior. And then we are going to assemble collections of those features and call it a vector space, and voila, Bob's my uncle. In point of fact, Bob is my uncle, but that's beside the point. Examples. These are easy things to compute. The end-to-end distance for a trajectory. That is, how far is it between the point where it took off and the point where it landed. That's interesting in its own right, as is the total distance traveled. How long did it, or how far did it go in the air before it got there? Put those together and you get something very interesting. A trajectory where the end-to-end distance is the same as the travel distance means it went in a straight line. A trajectory where the end-to-end distance is 0, but the travel distance is large, means it did something out there. Maybe it went in a circle, maybe it didn't. We need better math to understand that, and we'll get to that in a few slides. Anyway, you can come up with a laundry list of these kinds of features, some more informative. The properties of the convex hull of the trajectory, which is the polygon that encloses all of the points in that trajectory, actually winds up being very expressive regarding what the trajectory did and where. Some of them less expressive. The start and the stop time, for example. Most civilian air traffic tends to happen on a pretty rigid schedule. You're either during the day, in which case you were a passenger flight, you are at dark clock at night, in which case you were a cargo flight, or you're a red-eye. That's about it. There are others. For one particular project, we came up with a list of a couple hundred of these. Not all of them are going to be useful. Almost all of them are going to be redundant, but you can invent them. So, take those feature vectors, which are just points in some n-dimensional space, and put together a query. Let's define a flight that avoids space as one that is at least 3 hours long, so it's been up there a while, is at least a couple thousand kilometers long, and has a total travel distance twice as large, at least twice as large, as the distance from end to end. So they're going from points A to point B, but they went way out of their way to get there. That's a very simple query to run against a set of points. And to our considerable surprise, we got back not just one trajectory, but a whole bunch of them. And sure enough, these look like they're avoiding something. Now I have to say, it looks like they're avoiding Indiana. I'm from Indiana. It's not that scary. But you know, when you see something like this, it's clear that something else is going on. I just happened for a different project to be downloading a continental US weather map every 30 minutes. All of these happened on the same day, July 10th, 2013. This storm system in the early morning started over here in Illinois and just swept across the Midwest. And sure enough, they were going way out of their way to avoid that, either detour to the west and south, or you can see several flights there going up around the mitten of Michigan to skip it that way. This, by the way, is one of the primary applications of algorithms to analytic problems where you've got a human in the loop. To draw the human's attention to something weird's going on here and there's a pattern to it, you might want to look for corroborating information. There are a lot of such queries we can do, but here's the thing. We came up with that query by hand. We came up with a category of flights that we were pretty sure existed, and we tried to think of what can we calculate that will reveal them. That's a great first step, but where we really want to go is automated classification of trajectories and automated detection of things that might be anomalies. We will never do a perfect job. We don't want to do a perfect job. We want to do enough of a good job to allow a human to say, okay, here's the interesting subset, which is 1 or 2% of the overall data set. Now we can investigate it by hand. I mentioned a moment ago that I would tell you about a method that lets you say more things about the wiggliness of a trajectory than just, yes, it's there. The method's called distance geometry. This shows up a lot in protein analysis because it can describe how much wiggle there is in a trajectory and where. Here's how it works. You start with a curve, which is step 1. I haven't drawn any data points on there because to a degree it doesn't matter. The next thing you do is impose your own sample points on that. 4, 5, 10, 100. You get to decide how many, and it affects the resolution of the features you can see. Step 3, which as a scientist in the field of applied laziness, I love. Throw away the curve. That makes life so much easier. All you've got left are the points that you computed on it. And step 4, compute the pairwise distance matrix between all those points. What you've done here is you've gone from the initial curve, which remember lives in that inconvenient metric space, down to a distance matrix, which is just a matrix. Treat it as a matrix, normalize it a bit, and what you get in step 8 is a vector that is a shape signature for it. I said pairwise distance. Well, consider the distance between points A and D, which are the beginning and the end of the trajectory. That is the ratio between the travel distance and the end-to-end distance. Consider the distance between points A and B. Well, that is that same ratio just for a small segment of the trajectory. So I can now tell you what part of the trajectory the wiggles are in and how big they are. Do I have any geometers in the audience? If I say translation invariant, does that mean anything? Okay. This signature has a few desirable properties. I can compute that signature for any trajectory and look for other signatures that are similar to that in the vector space. It will give me trajectories that are moved around in space. It doesn't care about their location. That means translation invariant. It gives me trajectories that are rotation invariant. The distance between a set of points does not change if you rotate those points all the same way. It is invariant under uniform scaling. If I can find a small trajectory that's a C, it'll have pretty much the same signature as a great big C. And it's invariant under reflection. This is an S to me, so I guess it's a 5 to you. That has the same trajectory, the signature, as its reflection. This is kind of the holy grail of computational geometry search techniques. It's invariant under rigid transformation. Personally, I still think this is black magic. My colleague is a physicist who did a lot of work in molecular biology, and he turned me on to this. He's explained it to me. I can derive this if I have to. I still think it's magic. Well, that signature is just a bunch of points in a row, right? That's a vector. It's in a vector space. We have 40 years of clustering techniques to work with that. I'm going to tell you about a particular clustering algorithm that is phenomenal for sets like that. It's called DBSCAN. And the reason it's phenomenal is, one, you don't have to tell it how many groups you're looking for. It figures that out on its own. So I couldn't tell you how many different air behaviors there are. I can just go and find out. Second, it has the notion of an outlier. Common clustering algorithms like k-means, which is the first one you learn in a data analysis class, will put every point into a cluster no matter what, even if it doesn't make sense. Well, this algorithm, points like n over there sitting out in the middle of nowhere, it'll say, yeah, this is just off on its own. You might want to ignore it or investigate it separately. It only needs two parameters. It needs a neighborhood density. Think of that as how many people make a crowd, and a neighborhood radius, which is how close do you have to be standing to your nearest neighbor in order to be part of the same crowd. We use a slightly different version that gives us a hierarchy of clusters instead of just one. It abstracts away one of those parameters, so we have even fewer choices to make. Like I said, applied laziness. It gets you an awfully long way. And it's pretty efficient. We've run this on anywhere from a couple days to about 2 weeks of non-trivial clusters, or non-trivial traffic. We have tried it at different numbers of points for the number of samples along that signature. And we ran it on a great big Linux system. It only ran on one core, but it had all the memory it wanted so that we could factor out system limitations in I/O. Here's what it told us. The bigger your data set, the larger your central cluster. At the same time, there are a lot of outliers, which tells us there is some very diverse behavior going on here. Before I go on, would anyone like to take a stab at what that largest cluster is?
More traffic routes?
I'm sorry?
The high-point traffic routes, the predefined traffic routes?
Yes, but it's slightly more generic than that. What's the most boring thing an airplane can do? It can go straight from point A to point B. That also happens to be the least expensive thing an aircraft can do because it's the route of least fuel. And expense matters tremendously if you are an aircraft operator. So the vast majority of the traffic in this data set is you take off, you probably turn once, you go straight, you probably turn again to get to your approach corridor, and you land. That's 95% or more of this data set. So yeah, we really do need that notion of outliers, and we really do need the ability to create unbalanced clusters. I don't want to spend any of my time on that 95% of the traffic that's dead boring. I want to find the interesting stuff. So, clustering by shape using the distance geometry measure I told you about. This is one cluster. Blue is the start, red is the end. You'll see that these are all kind of shallow C shaped. You can see different clusters by, you can see the same trajectories at different scales. There are those 4 or 5 great big ones going from Chicago over to, that's the New York area. You can see them flipped by orientation. The cluster from Chicago over to Detroit, yeah, it's still a C, but it's flipped upside down. You can see them rotated over in New England. Distance geometry is really pretty remarkable. We got this with 4 points. Most of these trajectories start off with several hundred points. And if we wanted to be able to distinguish things like holding patterns happening at various places, well, increase the number of points and you're good to go. Speaking of holding patterns, these are a little bit tricky to see, but each of these trajectories has a holding pattern near its end in the blue part toward the landing. They are slightly different in shape and extent, but what I can tell you numerically is that each of these trajectories has a certain amount of wiggle at a certain point in its path. We can do that numerically. Humans are pretty good at picking this out when they know what they're looking for, but as we saw with Chicago, if you're looking at a great big mess, you'll never spot it. Whereas, numerically, we can find these pretty quickly and say to the air traffic controller, to the planner, to the people in the ops room at the airport, hey, something's going on. Okay, the people in the ops room at the airport know this long before we do. Out and back, if you have a flight whose start to end distance is very small, whose travel distance is large, and whose convex hull, which remember is the polygon enclosing the whole thing, is narrow, they have gone out, they have realized, oh no, I forgot to turn off the iron. They have turned around and flown home. I don't know exactly why all of these people left the iron on at home, but as you can see, there are a lot of them.
Medical emergencies?
This is possible.
Are all those clustered around major airports? Because that could just be generalization traffic that takes off from a home airport and lands back at the home airport.
It could be. Certainly most of them are major airports. I don't see off the top of my head any that are obviously not, but clearly you and I should sit down in a room with a great big monitor and play with this for a while.
Is it daily data or?
I think this is a week of data. We did not tell the computer we're looking for out and back flights. This is a cluster that it just found using the criteria I told you about a few moments ago. This is the outlier class. This is the stuff that didn't fit into any other category. Well, when we look at this, we can see, oh yeah, there's structure there. Look up at the north end of Minnesota, and then down below that, you'll see flights that are that same north to south mapping pattern. These are just on one day. There are mapping flights absolutely everywhere around the country because these couple dozen Twin Otters are always up in the air updating the latest imagery. I can tell you for certain they haven't been around Albuquerque recently because if you have one of these flights go over while you were building your house, you can date it almost to the day. I really wish they would pick up my backyard now that it's been landscaped. Anyway, the other thing about this outlier class is, yes, there is structure in it that we can't distinguish. That says we need to run this clustering again with maybe different parameters, maybe slightly looser or tighter in different dimensions. However, we've reduced the data by a factor of 20, so we can do that inexpensively. We could even run it multiple times, look at it from different angles, and see what jumps out. And you will find interesting phenomena. Look here in eastern Washington. Lots of aircraft take off from here, just south of Seattle, fly out to eastern Washington, do stuff over southeastern Washington, and then land there. Now, to me, that's a mystery. When I asked someone who was a pilot, he said, oh yeah, that's Boeing's test field. Boeing's plant in Everett, Washington is along I-5 just south of Seattle. If you drive from Seattle Airport up into town, you will pass it. They take planes from there, fly them out to eastern Washington for qualification and testing and just their general checkout, fly around the southeast part of the state where, frankly, there's not much happening, and then take them back home. There's structure like that all over the nation. Except See here in southern Nevada? This is the excluded area surrounding Area 51. Now, there's probably stuff flying there, but I guarantee you it's not broadcasting on civilian frequencies. There are a couple more areas like that around the country, but that's the one that's fun to point out. I don't know if UFOs are even equipped with civilian transponders. Even if I did, exactly as Paul said, I couldn't tell you. I mentioned earlier that mapping flights all do pretty much exactly the same thing, and here you can see it. They are, dare I say, ridiculously consistent in how they fly these patterns. They don't have to be. It would be pretty straightforward to write an algorithm to pull out whatever segments of path they were flying. But no, these are pilots with a very high tolerance for boredom. Let me wrap up. Density-based clustering, which is the clustering idea that I told you about in DBSCAN, has to do with how many people are close to you and are you willing to call that a crowd. It works phenomenally in the right mathematical space like a vector space. But in order for it to work in a way that will make sense to you, you need relatively intuitive features that describe a trajectory. Distance geometry, where you start with a matrix of points and do the all pairs distance, is about as far as I can stretch intuition and still be able to explain it to someone who's not a physicist or a mathematician. Also, you need a way to explore large clusters. That 95% of the data that is the boring, straight flights, well, sometimes you really want to dig into that and find out what's going on. But if I give you 1 million flights and say, oh yeah, explore the 950,000 that I think are boring, I really haven't helped you very much. So you need not just the algorithm, not just a way to run it at scale, but a way to dig down into finer layers of structure. Also, when we're working on theoretical computer science or theoretical anything, we tend to work with just the math and leave the details of the actual problem as, oh no, that's an exercise for the end user. I reject that notion. Use everything you possibly can find about your target problem and your destination domain to cut down your search space, your problem, your possibilities, and the dimensions along which you slice it. So yes, straight trajectories are boring. So I throw away 95% of my data in confidence that it's not worth spending my time on. Also, there's a lot of duplication. Airlines make their money on flying the same set of routes day after day after day. They will pay people like us large sums of money, hint, hint, in order to find the smallest and most efficient set of routes that they can fly that way. Well, if I can identify those, then I've gained a lot of power. I can throw most of them away and try trajectoring, is that even a word? It needs to be. And try clustering each trajectory against all the others just once. So I've got Dallas to Raleigh-Durham represented once instead of like 20 times for every single day. This is not always easy to do because since the atmosphere is a distressingly dynamic entity, the trajectory is never precisely the same twice, and that doesn't even get into things like flight delays. Also, let's consider that trajectory on a day with good weather, so it just flies here to there and lands, and a day with bad weather, where it winds up holding not far from Asheville for an hour. Should those be the same? Should those be classified differently? How do you make that decision? The answer tends to be you find the person who cares and ask them if they want it to be different. Put these two things together and you have a strategy for analyzing a large, diverse set of data that comes from the real world. There are patterns, there are commonalities, you can find them. That's not enough. You have to incorporate what you know of the problem and what people care about in order to go from an algorithmic context to a real-world applied context. It is expensive to work with real data. It's hard to get. It takes a lot of effort to analyze and clean and curate. There is absolutely no substitute for working with real data. It is worth the investment. Here I shall conclude. Thank you all very much for your attention, and I believe we have time for questions. I have a treat for you if I get good questions, so ask away. Eddie.
Do you do much with AIS, the maritime?
I do. AIS data, it stands for, what is it? I don't remember. AIS is ship-to-ship transponder data that everyone in shallow waters is supposed to broadcast so that you avoid embarrassing incidents like, say, a Navy destroyer running into a fishing boat. It is different from ASDI in that there's no central aggregation point. So in order to get this data set, you have to purchase access from a company that has, no joke, given receivers to people around the world and say, hey, will you put this on top of your house? It is another remarkable data set. It has ID, timestamp, latitude, longitude for several 100,000 ships in shallow waters at time intervals between 2 seconds, which is what you're supposed to run if you are in a harbor and you have humans on board, to hours, which is what you get out toward the outer bounds of the detection radius. You can get this in shallow waters, like I mentioned, or if you know who to ask, you can get it for deep water as well. See, the signal will propagate about 75 miles on the surface. It'll also propagate up a lot farther. There are small satellites in orbit that listen to AIS data and will give them to you in the middle of the ocean, in the middle of nowhere. Now, early on, a couple people asked me, do you have altitude data? Do you use altitude data? Yes, I have it. No, I don't use it because I want these algorithms to work just as well for maritime data. But I found one really interesting thing when I started to apply distance geometry to it. Ships can do something that aircraft cannot. They can stop. There's no such thing as a holding pattern for a ship. It just stops. That leads to division by zero. Division by zero leads to unhappiness. What that tells me is that I need more interesting algorithms that don't make the assumption of constant non-zero velocity. It also showed me, through just looking at the data, that the traffic patterns in major harbors are amazing. They are very carefully structured. The control room for Singapore Harbor looks like the control room for any other gigantic airport around the world, with rather higher consequences because these things are of necessity right next to each other. Up in general airspace around the country, an air traffic controller will get in a great deal of trouble if two aircraft come within 2 miles of one another horizontally and 2,000 feet vertically at the same time. A 2-mile radius covers most of a large harbor, and yet you've probably got tens or hundreds of ships steaming around in there. And an aircraft can change course or altitude in a couple seconds if it really has to. Figure 10 seconds to affect a substantial heading change. A large supertanker takes 21 minutes to come from cruising speed to a stop. If they reverse the engines, risk damaging the drivetrain, crash stop, that goes down to 18 minutes. But to answer your question, yes, that is a very interesting data set.
2 questions.
Yes, sir.
One, where are you pulling the data from? Is it transponder-based, radar-based, ADSB? Where is the data set coming from?
ASDI is a separate data set from ADSB. I'll mention that in just a moment. ASDI is the legacy transponder system. Aircraft communicate to ground stations, typically by radar. Ground stations aggregate that data if the FAA. The FAA sends it out from a central aggregation
So
point.
it is radar data then, it's not.
Ultimately, it's radar data.
And then second, do you know the altitude limit on that? Because I know most radars don't work below 2,000 feet.
I believe that unless the aircraft broadcasts it itself, like little private plane squawking 1700, then I don't see much below 2,000 feet, except for the very last data point or two as an aircraft is coming in for a landing. Now, ADS-B, which you mentioned, ADS-B is the, quote, next generation, which means that most of the world except for the US has adopted it, collision avoidance system where aircraft talk to one another instead of everyone broadcasts to the ground and then the ground broadcasts back. It has, for my purposes collecting it, it has the same limits as AIS data. You have to have receivers all around the world to get the whole thing. But it also includes much richer information. The sampling rate's typically higher. I typically get the tail number of the aircraft, which is effectively its serial number, and I get all the earlier stuff. What I don't get, which is often a value-added feature for the ASDI data, is a string representing the exact route this guy's going to fly, his estimated departure and arrival, and actual departure and arrival times. I don't get a lot of the metadata that a third party could add onto that data stream, mostly because I'm not paying the right people for it. The thing about the ASDI data stream, which I really, really like, is if you ask the FAA and you're willing to set up a network connection to their security specifications, which are pretty reasonable, they'll give it to you for free. I like free. Other questions? Yes, sir.
How far back does the data set go? Like, what level of historic data can you pull?
How far back does the data set go and what level of history can I pull? That depends on who I get it from. Flight data sites have very little interest in aggregating historical data. You really don't care if Flight 1604 from Albuquerque to Dallas was on time 4 years ago. So they tend not to store it. Some research institutions and large airlines will store it forever, but it's a pain to give it to other people, so they usually won't. The real answer is as far back as you were collecting it. I have a couple years worth because, well, I was collecting it for a couple years. I'm trying to get my own connections set up so that I can get it continuously going forward. Ask me in about 5 years and I'll probably have an answer like, yeah, I've got 4.5 years of data. Yes, sir.
What is your best sampling rate?
My best sampling rate for air data is once per minute. Every aircraft, every 60 plus or minus 2 seconds. That's the optimum. It's pretty consistent. It's not universal. For maritime data, my very best is once every 2 seconds. Yes?
I do a very mathematical question. How knowing the shape of your flight path affects you as a passenger flying in a plane? Does it affect at all?
How does noise in the...
I don't know how knowing the shape of the path, the different clusters.
Okay, how does noise affect the...
No,
How does being aware of?
Oh, knowing. See, there's noise in the signal between there and here. And knowing the flight paths affecting... I'll tell you this, I really don't care about delays under 30 minutes anymore. Because once you look at that data picture, and especially what a gigantic mess the New York and DC areas are, it's a wonder that it works at all. If I miss my connection, yeah, I get a little bit unhappy, but a 15, 30-minute delay, I've got a good book with me. It's all the same. It is fun, though, to get in a holding pattern or run into some turbulence and think, I wonder if I can find this in the data tomorrow, or I wonder how common this really is.
Have you tried overlaying that visualization on any other layers, like the IFR charts, the sectionals, the 3D representations of airspace, the different things like that to get a different picture? how it looks and how air traffic is actually.
The question is, have I tried overlaying other layers on this display? Structure of the airspace, the IFR route map, which is a fascinating entity. The answer is yes, a little bit, and we're doing that now. So this is ongoing research. Some of the things we're chasing right now are fusing other data sources like weather maps, like the airspace chart, to figure out what structure can we find and explain using other things that are easy to get so that we can further reduce the class of anomalies. You should come work with me.
So, how does the sampling rate, like how many points on the route, how does it influence the results of the clustering in terms of like sensitivity?
Mm-hmm. Anna's question is, how does the sampling rate, do you mean for distance geometry or the original data?
Like when you put the
Right. How does the number of sample points we choose for distance geometry affect the clusters? It affects it in that the number of sample points we choose controls the fidelity of the features that we can resolve and reconstruct. So for that 4 sample point case, I can tell you that between these 2 points, the flight spent such and such distance in an ellipse. So recall that if you have 2 points and the sum of the distances between them, which is the maximum possible flight distance, that defines an ellipse. I can't tell you anything about what it did within that ellipse. All I can say is, yes, it's in here. So if I want to more finely constrain what it did, I have to have more sample points so that I have lots of little ellipses instead of one gigantic one. You can actually do slightly better than that because you've got non-local information from other points, but it's still an ellipse.
And have you seen like threshold? I'm more asking about the sensitivity of it. Like, was there at some point where when you didn't see anything more and it was just too expensive to?
So you're asking, let me repeat that back to make sure I've got it. Have we gone too far? Have we found where it bottoms out?
Yeah, if you like evaluated which sampling is like still efficient, optimal.
Have we found the best sampling rate? We
I
have
guess
not yet.
that's what you're looking for, but
Yeah, that's exactly the right answer. Is it depends on what we're looking for. And the answer to that question is no, we haven't found it yet. That also depends somewhat on what the user cares about. So if they only care about big things, then fine, we'll use just a couple points. If they care about little wiggles, we need to use an awful lot. We are close to 4:30, so I'm going to switch over to the treat I told you so that the folks at home can see it as well. This is...
that's the right question.
Oh yes, you asked the right questions. This is a day of air traffic. I'm going to turn down the lights so that you can see it better. The clock in the upper right-hand corner shows UTC. So this is about 11 p.m. West Coast time. If you look at San Francisco and Los Angeles, what you see are the red eyes leaving. Here we go. The colors on this are backwards, for which I apologize. Look at the Midwest. Indianapolis, Louisville, and Memphis. Those are UPS and FedEx hubs sending out all the aircraft with the next day air. Everything's landing in New York and DC right now. All the red eyes arriving. In a moment here, we're going to see there. The 6 a.m. flights from the East Coast heading west are all leaving. You will see the major hubs light up from east to west. Dallas is getting its first wave of incoming. Now they're all leaving. Dallas, Denver, Salt Lake, their first wave of flights is departing. Next, you will see there the 6 a.m. flights on the west coast heading east are going. I pity those folks. They didn't get any sleep and they're getting jet lagged. Now we're up and running for the day. You can see all the major hubs active here. You can sort of see their traffic patterns, especially for some place like Salt Lake City here that has a very distinctive one. You can see where flight lines cut across the ocean. This spot right here off of Virginia where flights are appearing out of nowhere and disappearing, that's Bermuda. We do not have data from Mexico. This data feed includes includes every U.S. territory and Canada, and flights coming to or leaving from the U.S. So in the evening, like that flight right there, that's headed to Europe. You'll also see a few that go straight north over the pole for places like Russia. We're coming up on late in the day, so you're going to see the East Coast go dark just the way it lit up early in the morning. And then you'll see that same thing happen. Now, the last wave of flights is landing right now. You'll see that same thing happen across the country. Here the last waves are leaving from Atlanta, Dallas, and Chicago. The last set of incoming flights. Most of the incoming flights here are landing at the FedEx and UPS hubs to get ready for the night's flights. And here we end right where we start, with the red eyes taking off from the West Coast. Thank you again for your attention.